IEI with distinguished contribution to engineering, infrastructure, and professional development. He serves as president of the Indian Institution of Engineers India in 2016 to 17 and continues to contribute as past president. He is currently the National Member, Executive Council, WFEO, and Chairman, IMC WFEO, playing a pivotal role in global engineering cooperation with over 2 decades of dedicated service to IEI and leadership in WFEO, FIEAP, FIAP, and CEC. Mr. Vasoya is also known for promoting sustainable rural development and inspiring youth towards technical education. I would like to call upon Mr. Vasoya on the dais, please.
Good morning, all. I'm audible?
Yes, sir, you are.
So, respected colleagues and friends from around the globe, I am honored to address you today at the inauguration of Rainforest 2025, a flagship international event hosted by the Institution of Engineers India under the aegis of WFEO. As the chairman of the Indian Member Committee of WFEO, I take great pride in the fact that we are coming together not just as engineers, but as global problem solvers. The world today faces multifaceted challenges: climate unpredictability, land degradation, resource scarcity, and increasing demand for reliable infrastructure. But with challenges comes opportunity. Events like Rainforest 2025 give us the platform to channel innovation into impact by sharing knowledge, showcasing solutions, and stimulating collaborations. I am pleased to see topics like geosynthesis, IoT-based early warning systems, and sustainable construction taking center stage. These are key to building infrastructure that can endure environmental shocks and support circular economic models. WFEO strongly advocates for such forums where engineering meets policy, practice, and people. I extend my warm wishes for a successful conference and assure you of WFEO's continued support in promoting resilient and ethical engineering. Let this be a journey towards global cooperations, innovations, and sustainable development. Here, I would like to thank the President WFEO, who has delivered his speech through video. And I also would like to thank our eminent engineer, past president, and the chairman of CIC in WFEO, Mr. S.S. Rathore, who has also joined this seminar, along with the president, the Institution of Engineers India. I thank you all and my good luck to the seminar. Thank you. Thank you all.
Thank you so much, sir, for your kind words. So now moving to the third speaker of the inaugural session, which is Mr. VB Singh, President IEI. So Engineer VB Singh, an accomplished civil engineer from IIT Roorkee and a legal expert, was elected President of the Institution of Engineers India for 2024 and 2025. With nearly 40 years of service in Uttar Pradesh Power Corporation, he has held a senior technical position and contributed significantly to the power infrastructure. Mr. Singh is also known for his commitment to water resource management and engineering governance. As president, he envisions strengthening IEI's national impact, financial sustainability, industry academia linkage, and support to IMIE students. So I would like to invite Mr. VB Singh.
Thank you, Mr. Pathak. Good morning, ladies and gentlemen. Let me first thank our President WFEO, Mr. Mustafa Shehu, for his message. And I'm also thankful and welcome our Padam Shri S.S. Rathore Sahab, who is chairman of the IMC WFEU, and also Mr. Naveen Chand Vasoya, member of the Executive Council, WFEU, who has very kindly graced the occasion, and Mr. Vasoya has also addressed us. Thank you so much. It is a proud moment for me to welcome you all to Reinforce 2025, the International Virtual Conference on Resilient Engineering Innovations for a Future-Oriented, Reliable and Circular Economy Infrastructure, being organized by the Institution of Engineers India in association with McAfee and under the esteemed aegis of the World Federation of Engineering Organizations. The Institution of Engineers has always been committed to advancing engineering knowledge, fostering collaboration, and empowering professionals. This two-day global conference reflects that spirit, bringing together brilliant minds from academia, industry, and policy to discuss how we can make infrastructure smarter, safer, and more sustainable in the face of climate change, rapid urbanization, and resource constraints. Over the next 2 days, we will hear pioneering insights into geotechnical innovations, digital transformation, erosion control, bioengineering, and circular economy approaches. These are not just technical discussions. They represent our shared responsibility as engineers to build a world that is not only resilient but also inclusive and future ready. Let us use Reinforce 2025 as a platform to exchange ideas, forge new partnerships, and reaffirm our collective vision for engineering a better tomorrow. I wish the event a great success and look forward to meaningful deliberations. Thank you. Thanks to all.
Thank you so much, sir. Thank you for the energetic brief. So now I would, moving on, next I would like to invite Mr. N.K. Panda, Managing Director for India and Nepal at McAfee Environmental Solutions Private Limited, which is a subsidiary of Officina McAfee, SRL India. So to share his insights on McAfee's India's role in advancing geotechnical solutions for resilient infrastructure, Mr. N.K. Panda, an alumnus of FMS Delhi and BET Mesra, brings deep expertise in leading business transformation and large-scale engineering ventures. Now, I would like to call upon Mr. N.K. Panda on the dais, please.
Ratnakar, am I audible?
Yes,
you are.
okay.
Perfect. Very good morning to all of you, and great start to the day. It's a real pleasure to welcome you all to Reinforce 2025. I must admit, when I saw the topics and the renowned speakers, this is pretty impressive list. It's really pretty excited to open what promises to be 2 days of insightful discussions, fresh perspectives, and a shared commitment to sustainable infrastructure. McAfee, this is core to McAfee. Here at McAfee, we just don't build infrastructure, we build solutions. Solutions that are resilient, smarter, and more sustainable. As infrastructure accelerates at an unprecedented pace, we have a huge responsibility, the responsibility to use our resources wisely and to protect our environment and to build for the long term. This is where the geotechnical innovation makes a real difference. From the reinforced soil structures to rockfall protection to pavement stabilizations and to many other solutions, all our solutions are designed not only to address these complex engineering challenges, but also to minimize the environmental impact. In many of our projects, we have reduced the use of traditional materials like concrete and aggregate, which is helping to lower the carbon emissions and also to cut the construction cost as much as by 50%. So I once again welcome you all to Reinforce 2025. This is a huge step towards realizing this shared goal. Let's make this 2 days count. And also, I would like to congratulate and thank Institution of Engineers, World Federation of Engineering Organizations, the keynote speakers, the professors of various eminent institutions, to all the participants, and to our sponsors, namely Gujarat Metro Rail Corporation, Gujarat Maritime Board, and to all of you who are here, who have a strong belief that infrastructure has to be greener, more efficient, and more resilient. So let's build it smarter, let's build it greener, and let's build it together. With that, I welcome all of you, and a big thanks to all of you. Thank you.
Thank you, Mr. Panda. Thank you for the inspiring address. Now, quickly moving on to the next speaker that we have, which is I would like to invite Mr. Pietro Arbaci, Chief Marketing Officer for Officine McAfee, Italy, who will share McAfee's global approach on sustainability. Mr. Arbaci, alumnus of top-tier MBA, SRD at Barclays, and 15 years of professional experience in multinational corporation like McAfee, Microsoft, Facebook, and consultancy industry, with solid experience in creation, organization, and management of marketing and communication teams, and the management of complex strategic projects with like multi-countries and multi-departments. So I would like to call upon Mr. Arbaci.
Thank you. Thank you so much. Namaste and good morning, everyone. It's a pleasure to be here with you at Rainforce 2025, and I think this event is special, not only for the expertise gathered, but for the important conversation we will share, okay, over the next 2 days about how to create a more resilient and sustainable future. Let me briefly introduce you what McAfee does. We protect people, we protect infrastructure, community, and ecosystem through, let's say, future-ready innovation. We have operations in more than 100 countries and more than 140 years of engineering excellence. And we are at the forefront of climate change adaptation. So basically what we are really focused on is an integrated and sustainable approach to deliver solutions as was already introduced by my colleague. Today, McAfee is a truly global platform for sustainable infrastructure, and we operate through more than 70 subsidiaries and 20 plus factories across the world, with more than 3,500 colleagues. We want to deliver the most advanced environmental friendly solution in all the engineering, civil engineering field, from retaining walls and hydraulic works to rockfall mitigation and soil enforcement. We are doing engineering, but we are also doing some other initiatives that help us to spread our commitment to innovation and sustainability. One of them is Futura. McAfee Futura is a project that started last year in partnership with a sailor, Luca Rossetti sailor, and together with him we have built a very innovative Class 40 yacht that combines performance, that respect the environment, and basically we did it together with some of the most, let's say, important artisans around the world. It's not just why I'm talking about it today. It's not just a performance project, a sport project, but it wants to be also a sort of floating scientific lab. So together with some international university, we started to collect through this racing boat real-time data to monitor marine ecosystem and trying to support research and above all citizen science. So this is just an example, a symbol of our vision, raising awareness about climate change, biodiversity, and in this particular case, ocean health, and try to promote a model where technology and nature can thrive together. So thank you for joining us. I'm really looking forward to the ideas and the inspiration that Rainforce 2025 will spark, and as also my colleague and Key Panda said, let's build better together. Thank you.
Thank you, Mr. Arbachi, for your thoughts and continued leadership. So now moving on to the other speaker that we have. So now I would like to invite Dr. Ratnakar R. Mahajan, Regional Technical Manager at McAfee for ICAP, India, Southeast Asia and Pacific region. Dr. Mahajan leads geotechnical initiative across India, Southeast and Pacific region. He's an IIT Bombay alumnus. He specializes in soil reinforcement, ground improvement, and contribute to BIS, IRC, and ISS MGE. So I would like to call upon Dr. Ratnakar.
Yeah, very good morning to all. First of all, my thanks to all the speakers who have agreed for the delivering the talk. Basically, I'm sure the audience are going to enjoy the depth of knowledge and the beautiful content which will be delivered during this conference. And the idea of this conference started a few months back when Mr. Tanmay Chakravarti discussed with us like there was one successful event in the past, which was online event, and IIA was very much interested if certain event with, let's say, a focus on sustainability can be done. So I think I thank all the people involved in this event, especially from IIA, McAfee, as well as WFEO for agreeing for this event. And I think after COVID, we have learned how to connect online, and even 2 days conference, online conference can be conducted on this. This gives an example. Yes, now we are learning. As a civil engineer, we are mostly present on sites, doing construction, of course, and offices, but even we can connect on site through the technology of the network. So thank you all the best, and let's hope we fulfill your expectations in terms of the content.
Thank you, Dr. Ratnakar, for your thoughts. So now we will moving on to the session which everyone was waiting for, which is the technical session. And to open this technical session, I would like to, it is my honor to invite Dr. GL Sivakumar Babu, an eminent geotechnical engineer, educator, and researcher at IISc Bangalore, having over 400 publications, global recognitions, leadership roles, and major contribution in geosynthetic forensics and geoenvironmental engineering to deliver the official welcome note. And on this, I would like to call upon Dr. Babu to say a few words.
Good morning to all of you. I'm delighted that we're all meeting here on the important topic on the sustainability in geotechnical engineering. It's quite important because we have the complex issues such as climate change, rapid urbanization, and diminishing natural resources. And when you have these construction activities that need to be taken up on a large scale, we need to have environmental responsibility integrated with good engineering decisions. When you want to strike a balance, a lot of work is required, but it's very essential. And this particular platform, what you call Reinforce 2025, is an excellent initiative that was brought about. And good to see that we have a lot of academia, industry, and policymakers to collectively address these issues. And we need to really look at a lot of alternative materials and recycled materials like fly ash, polymer, and industrial products, and even the construction, waste debris. C&D waste, you can recover a lot of material. And the topic that we talk about, both sustainability as well as circular economy, they go hand in hand with the implementation of some of these technologies very well. So the geosynthetic technology itself is quite, very, very environmentally friendly and sustainable. But added to that, if you're able to look at from the point of circular economy and sustainability, it means a lot in terms of trying to show that the material consumption is less and then improve long-term performance. This is what we want. And so we need to really look at life cycle costs analysis. For design, durability, maintenance, and all of this, and also more environmental impact. And other thing that we seem to look at is the twins. when the instrumentation is required, particularly when you're trying to look at critical infrastructure projects, data analytics. There are a lot of things that are happening on construction industry, and there is a need to bring them together to really achieve this sort of sustainability in geotechnical engineering or infrastructure engineering practice. I'm sure that this particular two-day session that we have, you have eminent speakers. All of them did very good work in sustainable engineering, and the deliberations will be very, very useful. So I'm sure about it. So thank you all for giving me the opportunity. Thank you.
Thank you, Dr. Babu, for setting the tone for the sessions ahead that we have. So now we have another session which is planned, which will be presented by Dr. GL Babu on climate resilient design of highways and embankment using geosynthetics. So you may share your screen, sir.
Yeah.
And then.
Is it okay?
Yes.
Yeah, full screen, right?
Yes, it's on full screen now.
Yeah. First of all, I think I'm very excited to talk about this important topic where we need to really understand how this climate is impacting and how do you really rehabilitate sometimes. Failures are common sometimes because if you don't address some of the issues, we also need to look at rehabilitation as well. So how are you trying to talk about these issues is something that I would like to present here. It's a contribution from some of my students, Dr. Rakshanda, and Nikhil, and Professor and Dr. Shubham. I would like to talk about the need for analysis, the climate change, and Indian impacts, and stability of embankments. Of course, I'll also talk about some payments, design, and all of that. We know that the embankment structures are the most common type of structures. Like we see, then the response is affected by climatic factors, like whether it is for transportation infrastructure such as pavement, roads, or highways, or even water structures, water storage structures. I mean, they're all quite important. But what I see is that the codes do not address them adequately. And the stability that we want to see, like we talk in terms of the factor of safety and deformation, how much of settlements they can go, all that, and the various climatic conditions are very, very important. And we need to understand them properly if you want to really have a good, resilient structures. And I don't mind telling that the IRC codes and railway codes also do not address them sufficiently enough. And there are also many failures that we have been seeing. There is no doubt about it. Here you see some sort of pumping failure in a mud pumping failure, in a railway embankment where the bottom soil comes up to the aggregate material. And in some cases, we see settlements in embankments. It's quite common. This is a failure due to the embankment, the failure in the embankment because there is a water storage, and when you withdraw the water, there is a sudden force, the withdrawal force that's applied, and if the embankment is not compacted properly, it can lead to failure. So this is another thing that I just want to show, that your two-lane highway expanded to four-lane highway. This is something that we all want, but if there is no proper geotechnical engineering, it can lead to failures. So, for example, this is one case where they thought that there is a pavement failure. They used geocells, but then actually the underground, the bottom soil was not really was not good. Why? Because they made it into four-lane, but the soil below the the portion where they expanded that highway was not in good condition. So it led to the slope stability failure. It's not a bearing capacity failure. So there is a lot of understanding of failure mechanics, the type of soil behavior. All of this is very important. And of course, the good engineering practices need good understanding of the material behavior, right? All of these materials, whether it's concrete, soil, or steel, or whatever, we need to understand the material behavior properly, and that's important. So this is actually the way that after that it has failed, we're able to rehabilitate completely with a series of ground improvement techniques with the geocells and all of that, and trying to increase the bearing capacity at the bottom with stone columns and all of that. So we should realize that the embankments, though the courts are giving some sort of guidelines, they need to be, we should be able to understand some sort of issues, challenges. It cannot be same. The soil condition cannot be same along maybe a few kilometers of highways. There could be varying ground conditions, varying water conditions. Where the groundwater conditions could be completely different. So the important thing is that even the frequent failures also lead to high carbon emissions. When you're trying to talk about sustainability, we need to really avoid failures and see that we don't have carbon emissions because of that. And one thing that in geotechnical engineering is that the first principle is that the compaction. If the soil is not compacted well, then we will have a problem. And we should realize that embankment materials need very good compaction. And when you compact the soil in the initial state, it is unsaturated. What it means is that we assume that the saturation is not complete because we are pumping in some sort of air into because of the compaction. There is some sort of unsaturation. And if the unsaturation is there, that really helps because, normally we do the designs for saturated soils, but unsaturated state helps. And if you want to understand the climate resilient design, the climate induces a lot of variations in water tables, rainfall effects, and all of that. So if you want to provide a climate resilient design, we must be able to understand the variation of rainfall patterns, water table variations, and all of that, right? So that's important. And so the climate resilient design and analysis of embankments is important. Particularly when you have a doubt, it should be done. And what is this climate change? Actually, what is happening is that, yes, we know about climate change in a vague way, but actually definition is that the climate change refers to the shift in the daily, seasonal, and interannual temperature and weather. Both rainfall patterns and weather patterns do change. And why this is happening is that the carbon emissions that are there in the atmosphere lead to these changes. So people have looked at carbon emission, the CO2 concentrations in the atmosphere, and they felt that 450 ppm. If you see the y-axis, it's about 400 to 1200 is there ppm. It's about 450 or less than close to 400 or something. It's good because that was there earlier. And if you really try to do a lot of activities that if you don't really have sustainable practices, the CO2 emissions they're going to increase, and they're represented by their concentration pathway. We call it as concentration pathways. IPCC has given this 8.5. But if you're able to, have a sustainability based measures very, very effectively, optimistically, we can say that it's RCP 2.6 means that actually it is this the number 2.6 or 8.5 refers to some sort of radiation that happens because of the atmospheric effects. But for us to simply understand that it's more about CO2 emissions is something that we should understand, and we should do sustainable engineering practices. What is that? It is that suppose you have RCP 8.5, it means it's a very serious one, and we are still, the way that it is practiced is that we are not putting enough efforts. So you are using coal-fired power, cars and trucks with petrol. And because of that leads to temperature rise of about 3.7 degrees, which is quite high, and sea rise of 0.63 meters. And then extreme weather conditions do happen. And if you want to provide adaptation measures, that's going to be quite expensive. Like, you can't have ACs everywhere. You can't, it's very big, becomes very expensive. Whereas RCP 2.6 means at the bottom, you can see that, like, it's about renewable options like solar energy, wind energy, and all of that. Emission capture as well. And so you can use bicycle transport, and temperature rises are not much, 1 degree. And then sea level rises, particularly in coastal areas, this is quite important. So the adaptation costs are also low. So this is what I was just mentioning, that the radiative forcing function, this is the one, what is it, 2.6 or 8.5, this is a term. So people have predicted that if you, don't have this sort of sustainable measures, the temperature is going to increase, the precipitation patterns are going to change. That's what this shows. And the problem that we have because of this is that the carbon emissions, this particular, the bar on the extreme right side gives the carbon emissions. This is the latest document, which I took from one of the documents. Carbon emissions due to transport is about 15%, which is quite high. So if you're able to look at reduce the carbon emissions, the overall emissions are quite high, but 15% is something quite good number. Of course, you have power and other things as well. So I think it's quite significant. Now I'll come back to compacted soils. See, the compaction is there everywhere, whether it's a road structure, whether it's an embankment structure. We need good strength from the soil. And this is some sort of relationship which will tell you that if you compact it poorly, the degree of saturation will be low. Okay. So if you add water, it collapses a lot. Okay, it collapses a lot. This is valid for different types of soils. And if the compaction is good, if the degree of saturation is say 85% or 90%, then it can maximum go up to 95. So that 5% difference is quite less. So you can have settlements little less controlled, little better. Whereas if the degree of saturation is maybe 60% or something, that could lead to problems. Like 60 to 100 or 90% will be a big difference, because when the rain comes, inundation takes place. What happens is that because of unsaturation, there is what is called negative pore pressure, like capillarity, we call it capillarity, that becomes zero. All capillary forces become zero because the negative pore pressure becomes zero. So this climate change, how is it affecting? Because as I just mentioned, the erratic rainfall patterns can reduce soil strength, because earlier we did compaction because we wanted the negative pore pressure to be there and we wanted the strength to be there. Okay, so but then completely there is a big difference, and it leads to shear strength being less compared to previous time, and factor of safety is less. How does the factor of safety change? Second thing is the serviceability. Like maybe depending on the type of structure, maybe if you want a high-speed railway and all that, you need a very, very deformation restriction is quite stringent. But if you have a very poor compaction, in fact, I have seen we have seen in some of the railways that when we measure the shear velocities at the top of the embankment, they're quite low, which means that the compaction was poor. But then our compaction techniques are not very good, though they're there in specifications, they're not checked properly. So that led to downgrading of the speed to maybe 10 kilometers per hour, and it is supposed to be 80 kilometers per hour. That's the thing. So that is what it means by serviceability change. And so though we are interested in settlements and factors of safety, we should really understand how the hydrological cycle is affecting. Okay, like that is actually the loads on the embankments, the climatic loads. And there is also possibility of a lot of erosion, internal piping and all, because soil is something very, very variable, and gradation characteristics are different. So it's fluctuating, water table fluctuates. That's another issue. So what we are doing? I mean, are we doing it properly? I mean, I don't mind telling that we are not doing very okay, in the sense that we need to have what is called in IDF curves. What is that for the climate change or intensity, duration, frequency relationship of the rainfall patterns? So suppose you assume that the embankment, you wanted to see that it lasts for about 50 years. So 50 years, I should have the rainfall patterns. Maybe fortunately, we have the IMD. IMD gives all of that. And we must be able to construct this, take the data from them and understand the intensity, duration, frequency. If you want to do a pavement road, why a lot of flooding is happening in roads in India is because we don't even understand. Conventional engineers, they may understand about aggregates, roads, and pavement materials and concrete and all that. When it comes to rainfall patterns, absolutely they're clueless, except that they know that rainfall patterns have increased, nothing else. But how much is the increase if you want to understand, or what is the actual rainfall pattern, because the flooding occurs because of the water, the pore pressures that are generated, and the water is in excess of what is there, what the pores can occupy in soil. So that leads to, so we should understand what is called intensity, duration, frequency relationship. For maybe if you want to look at 100-year return period for your lifetime, you say 100 years or 120 years for reinforced soil structures. I must be able to have the data for at least 100 years, or look at what's going to happen if I impose that rainfall pattern. What is happening is that now the intensity of rainfall is so high, I take it as a load and then apply it on the top of the embankment. And if the embankment cannot take it, okay, then it fails. So that we should be able to understand. So those things are clear because we know the porosity of the soil, and how much of water can infiltrate and how much excess flow can be there. All of that is possible. So other thing is IDF curves are required, whether it is whether you want climate change or no climate change. But then when the climate change is there, these rainfall patterns are changing. So fortunately, climate change is a well-studied area, and people know that climate change can be predicted. So hydrological cycles are changing, but there is enough science available using what is called global circulation models. So we use this global circulation models, apply. Hello, am I audible?
Yes, sir, you're audible.
Okay.
Yeah.
Okay. So I had a doubt. Okay, thank you. So the other thing is that the GCMs need to be corrected. Say, for example, if you're trying to design for a drainage for an airport or a constituency, you must be able to understand what is the IDF curves there and how is it being affected by climate change. There are some simple methods available. Any of the water resource people will be able to help us. And this is a simple example of some of the sites. Say, for example, I was looking at what does it mean by climate change. The intensity will change by 10% or 15%. It depends on the the type of the design of the structure, the life period. Like if I say I want 30-year return, 30 year is the life of the structure, so I should take the data for 30 years and look at. I should get the IDF curve for 30 years with climate change and without climate change, and I see the difference. We have done that type of analysis for different return periods, and we clearly see that there are differences as high as 30 to 25 to 30% or 10%, 20%. It varies. So if you're able to compute this and understand this, then you can solve the problem. That's what I meant. Okay. So this is an example for Bangalore where we're trying to look at different return periods, and this is an equation of the idea of thing. Like it talks about intensity, duration, and frequency. So one can get this without climate change and whatever. And it's very clear that intensity of rainfall is higher. Everybody knows, but how much more and what is the return period that we are interested? That is what we should decide. Okay. So other thing that when we understand the climate change part is clear now, of course, we can really, there's a lot of knowledge available. We don't need to worry that that's the problem. Second thing is this soil mechanics. Okay, I think most of the engineers know about geotechnical engineering, at least. So they know about effective stress of Terzaghi. Unlike, suppose a load is applied on a material in a concrete or steel, the load is completely transferred to the internal matter, like grains or solid continuum. At least in steel and concrete are continuum. There are no pores there. But in soils, what is happening is that there are pores. So the pores are there, water is there in the pores. So the thing is that the total stress, whatever you apply, is that total stress minus pore pressure is called effective stress, because it's like a BP, BP sugar, right? For us, BP is actually. So it's similar to blood pressure, and it creates a lot of problems. So, and then that is what we understand. But when it is, as I said, compacted samples are unsaturated, and we do unsaturated, we need unsaturated state because we want good strength. But the negative pore pressure, in fact, what happens during rainfall is that the negative pore pressure slowly becomes positive, and after that, because positive pore pressures will be higher, and after that, excess water will also, the drainage happens. All our roads become drains. that what we see. So the negative pore pressure is quite important that we should understand. So I just want to tell you that the negative pore pressure, again, how different soils will have what is called soil water characteristic curves are there. This is also like, many of the people in agriculture engineering, they measure, but not much in geotechnical engineering, because in agriculture engineering, people need what is the minimum water content and what is the maximum water content. So it is called soil water characteristic curve. The same data you can use here, because when you are using it for cultivating, the material, things, you can always use the same knowledge in the embankment design as well. So for different types of soils, the water content versus matrix section is this. Matrix section is nothing but negative pore pressure, and that is important. Okay. Other thing that nowadays that's become important is that if you want a very good engineering practice, people have to use good tools also. It's not like only a textbooks that are available and go by simple concepts. We use what is called Mohr-Coulomb model. So because we want for calculation of factor of safety C5 gamma, that's what the code says. But if you want settlements, because we want to understand settlements, right? So the settlements are given by modulus of the soil. So modulus of the soil can be found out in all the tests that we do. That should be reported. Actually, if you look at some of the reports that you see for embankment design, they don't tell anything. I mean, I'm sure many people do a structural design very carefully, but then when it comes to geotechnical design, there are challenges. So you need to calculate factor of safety as well as deformation. How much of deformation that the embankment can have, because we are compacting it in lifts and the rollers are there and all of that. There are a lot of things that are happening in the field, but by simple things will not give that information. So there are a lot of advancements that are there and knowledge is there, but unfortunately it's not being used in enough, but others are doing, like, you go to UK and other places, they are doing it. So I was just mentioning that the compacted soil is unsaturated. So when the water is added, it collapses. That settlement also needs to be measured or predicted, but that is not mentioned in the codes. So what you are trying to do is that we are only knowing the consolidation settlement, like consolidation settlement under load. But we don't consider the settlement due to collapse. It can be even heaving also, depending on the level of compaction. If the compaction is very good, then the settlements are minimum. And if the compaction is poor, then it can lead to problems. So that to understand, we have a lot of advances like in Spain and other places. I just don't want to tell. If somebody wants, I can tell them later. But there are methods available. This is an example of predicting collapse due to inundation at various stress levels, because stress level means the load applied on the embankment. So one can do, we call it what's called Barcelona model, and some of them with geotechnical engineering advanced knowledge can understand this. But for normal people, you can always go to some NIT or IIT. They'll be able to help you. And so there is also called anisotropy, because on the wet side and dry side, the type of soil state is different. One is, it will have we call it anisotropic fabric. So that's also there. So what happens? Because of these advances, they're available. So these are all some validations that we have done, and in fact, this is what the model gives. Depending on the degree of saturation, I can find out the stress strain response. This is what I want ideally, because we know that assuming that the soil is saturated is not sufficient. Assuming that the degree of saturation, say for example, here is 0.8. You can see that the strength of the soil is more at different strain levels. They're all at different strain levels. The strength is more if it is unsaturated. And if it's saturated, all that strength reduces, settlement happens. So how much is that is what you need, and it can be predicted. This is a simple example that I have given in an embankment of 10 meters high. And so we're trying to model this, 1:2 slope and all of that. We're able to clearly see that in India, the rainfall patterns are, initially they'll be slow, and in certain duration they'll be very, in 3 or 4 days they'll be very severe, and there you will see a lot of problems and news, all the news in in September, October, we'll have a lot of embankment failures. Whether it's highway embankment, it's railway embankment, we're all surprised. We're not surprised, but it's not correct. Now, we need to reduce those failures, and these are all some results. What happens to the displacement or the compaction settlements due to different rainfalls, and also this is a degree of saturation. Right? Initially, degree of saturation is lower, like 0.4, 0.5 or something. It slowly becomes close to saturation at the bottom levels and all that, like that. That's what it gives. And this is some idea of displacements, a deterministic design. We call it factor of safety based design. Other thing, some of the engineers should understand is that, we use factors of safety in design. For example, if the factor of safety of 1.5 or 2, it means is that your 100%, variability, like you're taking care of like factor. If the factor of safety is variable, why I'm telling the factor of safety is variable is that even in the structural design, any of the parameters, whether it's a concrete strength or a soil strength, they're all variable. But maybe in concrete and aluminum and they're much less, maybe 10 to 15% maximum, and timber and all of that. But when it comes to soil, the variation is so high, like 30 to 40%, even 100%. And you finally say that, oh, I can't understand soil behavior. Okay, but no, you understand how much it is varying, you're okay. See, if you put that variability into design, it's okay. So soil properties are variable, concrete properties are variable, even the rainfall patterns they're variable. We are talking about climate change. Actually, they themselves are variable. And wind loads are variable. Earthquake loads are variable. So this is where our design practices have to improve significantly. And this is something that I was talking just now mentioned about. We don't have, say, if you measure the strength of any material on a beam or a column or something, it's not a unique number. There will be many numbers. And we have to understand which will be the number that you should take and what is the variability band. You call it band, and that needs to be understood so that it doesn't fail under the worst conditions also, or the probability of failure is very, very low. That's what we want. And in fact, these are all signatures of the ground, like we call it erratic. If the soil is erratic deposit, because properties are varying every half a meter or 1 meter. Signature will be like this, which is called autocorrelation, and like that. So we have to understand that even suppose there is a good contractor, he does a very good job on a highway, and the soil properties will be more or less good. Whatever you want, you will get, but there'll be some variation of maybe 10%. If there's a bad contractor, which I have myself seen quality control many times on highways and embankments, the variations are too huge. The compaction variation will be 30%, 40%. Can I allow it? Even the values do not match. So where do you do that? So we need to understand the variability. And one basic design philosophy that we are doing in civil engineering is that we want capacity should be more than the demand. When you have one, that means that factors should be more than one. That's fine. But giving a standard number like 1.5 or 2 or 1.2 or 1.1 will be tricky because if it fails, civil engineers are responsible. Money is lost for the government. So we have to understand how much more is sufficient, how much is required, because there is a lot of uncertainties like design decisions, contractor, and all of that. So we try to keep the probability of failure is very, very minimum. Okay, that's what we don't want to minimum, and this is all that risk-based designs. In fact, in India we should do this. Unfortunately, we're not doing it. And because risk also includes the cost consequences, like the other day there's a bridge failure in Gujarat, right? So maybe if a periodic inspection and strengthening may have avoided that, like retrofitting and all of that. So the risk includes the consequences in terms of the expected. You can calculate, like if we do it in many cases, how many losses, money lost is all that can be estimated. Reasonably estimated, and say that let us put more money into that so that there is no failure. Consequences are minimal. This is not a new one. This is a very old one. It is done in US 1984. They looked at all the failure of structures, dams, foundations, rigs, mine pit slopes, and they calculated the probability of failure associated, which should we use in design. And in fact, Australia and New Zealand commissioned large dams. They use this. The probability of failure has to be very, very low, like -3, 1 in 1,000 is what is acceptable. And if your factor of safety gives that 1.5 or 2, if you 1.5 gives, you're okay. But if it doesn't give, and no, if you insist on factor of safety, it's not correct. So I have to say that whether what is the factor of safety corresponding to probability of -3 has to be seen. So this is a discussion. So what I did was that here we are looking at probability of failure during first rainfall and second rainfall, it increases because the settlements will be a little more. First rainfall is a small steady rain, but when the intensity increases, it increases, like its deformation increases from 0.3 to 0.6, 0.4 or something. It is like 40 centimeters, right? 20 centimeters to 40 centimeters. It is big. We calculate. Like even this depends on our methods that we use. Like if you use a simple thing, you will not be able to estimate settlements properly. But I said there are two types of settlements. One is a consolidation settlement. The second one is a collapse settlements, because in the embankment, there'll be some, if your compaction is poor, there is a problem, right? So we know that there is an inundation, even roads, why it happens, why potholes, all this form. So this is there. So we can calculate the probabilities of failure. It's not known. So, okay, this is another interesting thing that I just want, because we are talking about reinforcement, right? So what I was just trying to show in this example is that geocomposite is something that's a very useful material in this thing. And we try to look at an embankment. We have a doubt that it may fail because of the climate change effects, maybe after next year or something. We want to see the bridge. The analysis is always required for every 2 years or 1 year. There should be some certain rules we have. So when you're first design may be all right, but during construction there could be some slips, or does it need any rehabilitation? We want to look at it. So that's what we do. The soil water characteristic curves of the composites are here. And we're trying to do the same design. The assumption here is that, see, the embankment is 10 meters. Now I try to put a geocomposite here, so that my problem because of the rainfall is that the drainage is not there. So pore pressures within the body of the embankments are increasing. Within the body of the embankment, the pore pressures are high. So factor of safety is less and the embankment fails. I don't want that. So I'll put the geocomposite here, and then remove all the water, infiltration water. So we did that, and you can see clearly that the pore pressures are distribution embankment geocomposite. They're all negative one. You can see very nice figure here, which is without geocomposite, you will see that the pore pressures are reaching at the bottom, particularly they are low, and nice slip circle failure occurs. But whereas if I put a geocomposite here, you'll clearly see that whether it's first rainfall, second rain, all that, they're all negative. This -25 kPa, right? So displacements are also controlled because the water is going out and there are no pore pressures. And this is a clear thing. The factor of safety, we want to see in the normal case, factor of safety continuously decreases, whereas here the factor of safety slightly decreases. Then at the moment the capillary barrier effect starts, the factor of safety increases and drainage goes. So factor of safety is whatever you need, or even reliability, both are there. So this is what is required. These are all some examples of calculations. So these are all some more calculations. And in fact, for different return periods, one can calculate. There's a beautiful example here that for different return periods, how the factors of safety change, and how they, with geocomposite, how the factor of safety will improve, right? This is an example. So what I just want to say is that, yes, climate resilient design, I think whoever is listening here, they know about something about it, how to reduce embankment failures in the country, and see that we do embankment rehabilitation also if required. And the methods of calculation are available. It's not, you don't need to worry, oh, there's a climate change, or we don't understand geotechnical engineering. Why? Because there's so much variability. No, everything is available. And understanding soil mechanics, unsaturated soil mechanics or saturated mechanics, they are important. When agricultural people are doing, which is there right from 100 years, in geotechnical engineering, they need to do it. So the settlement models also need to be correct. And as I showed, geocomposites will help a lot. The other thing that I want to show about payments is that, again, payment is something very, very roads, embankments and roads are quite important. We're able to do that for payments. And with roads, with geocomposites, they're quite helpful. And this is an example. We came up with a new concept called for the drainage design. I was mentioning about capacity and demand. What is given in IRC codes is that they give you some gradation, okay, like a GSB 1, 2, 3, 4, 5, 6. But we, when the rain comes, we should understand what is its permeability. Gradation alone is not sufficient. First, the gradation should be stable. It should not be internally clogging. And water should percolate nicely into the next drain. The drainage provision should be there. So what is happening is that we only give the gradation characteristics, but we don't know how much of capacity it has. See, the drainage capacity is there. And what is coming, load is nothing but the intensity of rainfall. If the intensity of rainfall is more, and if the pores are all occupied in the drainage medium, you have excess flow and flooding, right? So that needs to be understood. So we have come up with a method called capacity demand. It is a simple like factor of safety thing only. Like you should be able to understand the capacity of your drainage layer. We don't have it in many of the guidelines, right? IRC, like for everything we do, we know it's a common sense that the capacity should be more than the demand. But if you don't know the capacity of the drainage system, we'll not be able to understand whether it fails or not, or stays or not. So this we try to do. We constructed, intensity, duration, frequency relation with climate change. And what happens if it is 100 GSB? So the 100 GSB and with the capacity should be more than the demand. So you must be able to come up, you can see in this figure that the intensity of rainfall per hour, right? And you will see, you provide always, if they're depending on the duration, provide this higher. That's what we want, right? So in fact, you should do LCA, life cycle analysis. And we did that for different materials and all that. And it is very clear that, see, when you're talking about natural resources, ecosystem quality, this will definitely give that information, even human health. In fact, what is happening by repeated construction, a lot of dust is there, a lot of other issues are there. Human health is affected. So we want to, so there are methods. This is not new, any BTech student can do it. You tell them there are right software and all of that. So you can do that sustainability analysis. And here it shows that resource scarcity can be reduced by 50% with geocomposites. Human health can be improved by about 50, ecosystem, all of that. Impact reduction is quite good. So we are able to look at some of these things. And so these are all some more calculations of percentage reductions and all of that. And so it's found that geosynthetics lead to sustainable designs from both reinforcement and drainage considerations. Okay, so in pavement design, I think all embankment design, we need all of that. So thank you very much. Thank you. I hope it's okay. I'm sure if I'm not in time or just flow, it was a flow. Sorry if I am exceeded.
No, sir, it was perfectly fine. Thank you very much, Dr. Babu, for this very informative presentation on the importance of climate resilient design for our geotechnical structures as well as transportation infrastructure. So moving towards the second presentation of the day, that is on rockfall mitigation measures for hilly regions, I would like to invite Dr. Ashish Juneja, professor at IIT Bombay, specializing in dynamic soil behavior, underground structures, and ground improvement. An IIT Roorkee, IIT Delhi, and NUS alumnus, he is an acclaimed researcher, consultant, and award-winning teacher with global academic affiliation. Over to you, Dr. Juneja.
Yeah, thank you very much, Dr. Rupam, for the nice introduction.
Thank you, sir.
Good morning, sir, Professor Babu.
Good morning, Professor Juneja. It's a pleasure to meet you.
It's a pleasure to meet you, sir. And congratulations, sir, for this week's program.
Yeah, please join us.
I will definitely do that. Yeah. Thank you. Okay, just I need to share everything. Share entire screen.
Yes, sir, it's visible.
Okay, very good morning to you all. My name is Ashish Juneja. I'm here at IIT Bombay for last 20 plus years. But every year, every day, my experience and my learning curve gets better and better. So I would like to present today on something I've learned over the last few years on the mitigation measures, especially for hilly regions, because this is the region where Mumbai and the Maharashtra and entire western coast belt of Maharashtra lies. Before I continue, I hope you all can see my first slide.
So it's the title slide as of now, sir?
Yes, it's the title slide. I'll just move to the next one.
Yes,
So
sir, it's visible.
Yes, I have my major presentation today will be on the first case. So it's because I think that will pave the foundation on what really the work or the status of the work, which in fact the next three sites. So my first slide is on Lonavala. It's called a Monkey Hill Station. Okay, as the name sounds likely because of the tremendous amount of monkeys on that hill. We will look at what we have learned from this site, the failure and the past failure, and even the present failure, what we have seen. This will pave the understanding of what the next three, especially I would say the Dimapur Kohima National Highway 29, which was became very famous about 2 monsoons back. So I will speak on this. And of course, the more recent application on what a non-traditional method of application of these barrier systems are. So my topic runs from Monkey Hill, Lonavala Monkey Hill to triple waterfalls of Dimapur. That's and how vast or how strange the Indian subcontinent gives, what surprises does it give? So the very first one, Lonavala, it's famous if you are from this part of the world. In fact, Lonavala itself, by name itself, is famous because of the several movies which have been made. So this particular section, it runs from Karjat to Lonavala. It's a 28 kilometer route. It has 27 tunnels, too many. It has the range, Sahyadri range goes right up to 600-meter high, the hills of this entire range. It is unbroken, it is continuous. That is why you will find that several highways, they run parallel from north to south on either side of the range. So the connectivity between the ranges is pretty limited, and all these connectivities are subjected to various kind of failures especially during monsoon. During monsoon, the region receives over 3,000 millimeters of rainfall. This is huge. If you imagine that 100 millimeters of rainfall each day in 24 hours creates havoc for any urban city. It happens once in a monsoon period. That is what you hear, and it is becoming common over the last several years. Of course, because of the various what we hear about the change in weather over the recent decade. But 3,000 mm is huge, I tell you, and it falls continuously over a very short period of a few months. They carry vast quantity of eroded material, and this is what erosion, and this is what really makes it much prone to failure. And we are speaking about cliffs which contains rock. The rock is widely spaced joints, huge joints and pockets exist, and it is these joints, the material within the joints, which in fact is the one which makes it more difficult. Now, over here, what we did was we collected a lot of data from Central Railways, and fortunately, Railways did manage to save how much of where the particular landslide events have happened. All this quantity of the rock material which came down from the hills, they recorded the historical data. So I'm going to run a 20-second. I think it's not more than, oops, I'll pause over here, sorry. It's not more than, what do you call it, a few 20-second or odd video, but you can see the dots appearing. Each and every dot is a new rockfall or landslide event, depending upon the volume of the material which came down the hill. You are again looking at a stretch. This entire stretch is just a very short, about couple of kilometers. And what you're going to see is the stretch runs from Mumbai to Lonavala. This is a small 2-kilometer stretch. I'll just run it. You see the dots appearing. It had a background music. The music was quite airy, so I've just muted it to keep the mood normal in this group. You see the number of events, they keep increasing. And since 2011, more events have been happening more lately. So 2017 is what you see is a lot of dots, lots of colors coming up. And this particular stretch, what you see here in between. So it's this stretch. Oh, sorry, I made it disappear. I'll just drag it again. What you see, the stretch in the middle, is something which is the Monkey Hill. So it speaks about the how the site itself is quite danger to the railways. So this every year, in fact, railways, what they do is they have their what do you call help people. They walk along the track every morning. They cover kilometers of track each morning, and it is their job during monsoon, a very dangerous job, by the way, that they have to keep track of whatever material has fallen down overnight. And during the day itself, of course, they keep track of it. There's several whole aspect of people monitoring this visually on foot. And this particular incident in 2017, in fact, this was a wake-up call, because a huge boulder in July 2017, it fell into the, of course, the engine. No one was, there was no casualty in that, but what we saw was the engine itself was pushed off the track, and it costed railways too much, but of course, people were saved. But next month in August, there were people sitting in a bogie. The train was passing through another stretch. That is the Hubli LTT Express. And there was this boulder while the train was still moving. It punched through the roof. There were people having lunch, and it crashed through the roof onto them. It was a very danger, but fortunately, injuries did happen, but fortunately, there was no death. So I would say 2017 was the wake-up call for the railways. I'm sorry I zoomed in, but I'm trying to zoom out again. I do not know. It's okay. So this is 2018. So what you see are the two photographs. Just let me let you know about this. This is rare. These photographs never came out of the the media, but what it shows is just at the tunnel entrance, you see boulders fallen down. At another stretch, there's a huge boulder, which in fact on the right-hand side, which has been crushed into two pieces by the workers, and they're trying to move it away from the track. You can imagine these boulders, had a train been there, it would have been a major incident for the Central Railways. So like I said, this railway started to take seriously about this. So they no longer thought of having people alone walking. They wanted more technology to come in. And this was a time where they explored the rock mitigation methods. Just let me tell you what really this, the shaded region is the Monkey Hill. So this map itself is skewed by 90 degrees here. North is towards the left-hand side. So I just had to fit it on the slide. So pardon me for that. But what it shows is Monkey Hill, and Karjat is close to Mumbai. So you're running from Mumbai and you're moving towards Lonavala. That is the track. I think the blue track is the downward, meaning it Karjat to Lonavala, and the white track is the upward, which moves from the Lonavala to Karjat. The Himanki Hill is the one where on either side what you see is the tracks. The tracks, in fact, the blue color is the one which is more prone to rockfall. It's because of the nature or the what do you call it, the terrain, the geometry of the terrain. But this small 1 kilometer stretch was taken as an experimental area. Let's do something about it, but let's start with a pilot study of only 1 kilometer. So this is what people we started to work on. Okay, it's still not the complete site. Remember, it's just a sample site, and it was, I would say, randomness came into picture because of the experience that this Monkey Hill is a problematic site. Let me tell you a bit about this station itself, Monkey Hill. Here, it's a site where the train stops, literally stops, and a second engine is added to the train to pull the train up the hill. So it's, if you're going from Karjat to Lonavala, a train will stop at Monkey Hill, and you'll have another engine which just tags along to increase the traction. Like any others, like any other, what do you call it, problematic geotechnical site, we did a lot of investigations. And I think this, for at least for rockfall, and because usually slope itself is not a big thing, rather than more is like the material itself falling down from surface or near surface. So I would say this, you should look at this data with a pinch of salt, because if you look at it, the data itself suggests that, if I do a normal slope stability, it will show that, I have a very nice, I can have a slope which is, at a steep gradient, and nothing will happen. But let me just remind you, it is the joints between the rock and the material within the joint. So in this case, the residual soil, what you see, that probably is the one which is between the joints. So what you're saying is still a material which has some plasticity. That's the residual soil. This, of course, makes the residual soil more problematic. This soil, if you live along the western coast of the country, you will find that this soil is hard as rock when it is dry. So that's why you see down Kerala, people use this soil, a lot of this soil to make bricks. It's very solid. But once rain occurs 1 year, you'll find nothing happens. Second year, nothing happens. But kaboom, like, all of a sudden, after a few years, you'll find the slope, which was very stable, it just slides like, like a mud. And these kind of failures, what you have seen, which happened few years back, close to south towards Kerala, you have probably heard of villages being, washed off. This is the strange nature of the residual soil. What was done for the first time, again, drone survey was done. And I think as an engineer, that's the first lesson we should learn. We should not rely everything what you see at your eye level. You need to go really right up to the top, see everything, even if it is not an approachable, you'd use some kind of modern technology. In this case, we use digital maps. So we digitize the drone survey into make a 3D map. So it's you can see, visualize which where are in 3-dimensional, which are the likely paths of rockfall where it can occur, and which are the sections you need for further investigation. But of course, as shown over here on the first location, that is the first, the central photograph. It shows that even by to a lay person, the path which is shown by yellow line, it's quite likely the rockfall will occur along this path, and the disintegration, the debris flow follows its channel. The left-hand side photograph was the first identified location. It shows the top view of the drone or the bird's eye view of this thing. I think somewhere on the right side, you see 2 black lines on this photograph. Those you can't see them, I think, but there's a railway track on the where the crosses are. There are railway tracks somewhere there. And what it shows is that every 10 meters a section has been taken to see that this is the first vulnerable section. So in the next few slides, I'm going to run through a slope which has two gradients. The one above the red line, which you see on the left side figure, it has a steeper gradient of 80 degree, and the down one is 50 to 60 degrees. So what you see is a plane which is, has steep, pretty steep at the top, and again the steepness is still there towards the railway track, but the gradient reduces slightly. So these are again section 1. Like I said, I'll run through section 2. Section 2 is I think I made it double. Yeah, section. Oops. Yeah. Sorry, section 2, 3, what you see is again similar on the left-hand side. There are gradients, and what you see is, steepness changes. What is important is on the right side, what you see is, see in the oval shape, those are the ISMB sections which railways had used long time back. And what you see is because of the impact, all these sections were damaged, they're crooked at different angle. So this is again taken from far pictures, and there are several yellow lines on the right side which shows what are the likely tracks which the debris had followed during the downflow. There are several pictures. Of course, what you see is a lot of debris lying, which are of course dying to fall down. So this was a potential site which requires immediate clearance and then followed by protection. There are several other things we noticed. So railways had a rigid barrier installed. Now, rigid barrier, as even IRC recommends, it is part of the recommendation wherein you want the debris not to come to your track level. But what you see is the rigid barrier, although they are fantastic, they are expensive. But what you see is with one impact, what you see on the left-hand side, with a single impact, it gets damaged. It becomes useless. On the right-hand side, what you see is there's 4 impacts, 1, 2, 3, 4 yellow lines. With each impact, what you see is it gets damaged. So they are, in fact, good to some extent, but because of the lack of flexibility, they cannot really absorb the energy, and the whatever damage you see is reflected, and the boulder or whatever debris falls on them directly. Because they don't absorb it, it rebounds. So you need something which can absorb as well as which and does not allow the system or the debris to flow down. This is location 4. And location 4 is the one wherein, the Hubli LTT Express train, wherein people were having lunch in the train bogie, and suddenly a huge boulder fell down onto them. So this is that site, location 4. And similarly, we have location 5, wherein we got, through the digital images, of course, we pieced down what are the likely path and what are the length of stretch which needs further investigation. I hope my presentation is clear up to now. How are we doing with the time? It's 11:24. I hope people are there.
Yes, sir, it's perfectly fine, sir.
Because
We have
I
time.
can't see anyone, and I don't want to be the lone person speaking English. And then suddenly I realize one mad faculty professor is speaking to himself. So please be with. I will try to wind this up, but I just wanted to show the interesting section first.
Yes, sir, we have time. Yeah.
Let's look at it. So we have rockfall mitigation system, and we need to select the most effective one. If you look at any standard code, and you see that it is normally grouped into 3 different categories. One, you want to prevent. So prevent means you scale, you trim, and you actually remove all the loose debris. And if needed, you will also do some support to the rock by providing some anchors, and then and above the anchors you would probably shotcrete it to cover the or protect the surface from weather. As you see, the rock itself, once it's exposed to weather, it starts to decay, and the depth of decay increases. So shotcrete is more like to delay the decay. It's not a foolproof method, I would say, but of course you need to go back again year after year and see what really repair work is required. The second is the retention measure, wherein you would retain the sliding mass by using a mesh, a network of supports. Mesh, of course, will also require similar anchors and to support. And the third one is protection, meaning what happens if the debris starts to flow, and you need to prevent the debris to reach to your infrastructure, meaning either the roads or the railway track in this case. So you can have either barriers, that is the last one I've written, sheds, that's concrete shed. Like I said, this is one of the method, but it's expensive, and because of the rigidity, it prevents what do you call it, little absorption. But there are, of course, methods to increase the absorption by putting some kind of absorbing material at top of the shed. For example, people have tried using earthen embankment over them, or even rubber tires with earthen embankment. These are all methods of research, and I doubt whether your client will be happy with anything other than the codal provision. But nevertheless, this is quite a lot of work has been done, especially in the Zurich and other European nations. You can also have ditches in case there is space permitted. But in most of the sites which we have seen in this part, there is a lot of space constraint because of either the roads or the tracks are right next to the steep slope. So what we are saying is one method may not work. You need to have a combination of two or more methods, and it is the selection design which is important. This is more like, I would say, an experience rather than, I would say, a textbook problem to be solved. What you see is you need to have an experienced engineer who probably will not have the right answer immediately, because you need to have, like I said, all the survey, the drone survey, the reports, everything together to reach a conclusion. Now, I've copied this table right from IRC 23. That's Special Publication 23. It's a good table, and I really like it. What I see is right from, I don't want you to really read up what is written word by word, but what I would like you to appreciate is you run from top to bottom of the table. Firstly, the cost of the mitigation method shoots up drastically. That's one. And what you see on the leftmost column is the first one is very simple. And then as you go down, the complication starts to increase in terms of both design as well as implementation. So if you go down, if you first look at the top, trimming and scaling is the most easiest one. Then you have barriers. And if I go down, you actually at the last thing is code says is if nothing thinks so. In fact, this is an indirect way of what code is trying to say is you move from top to bottom. If one doesn't work, go down to the next one. If the next one doesn't work, go down to the third one. It's that way, right? So if you look at it as a person who just wants to look at the table superficially, it says a rock shed has very high cost. And of course, if you are suggesting this, you have to show that all the remaining methods will not work for your site. So this is, of course, an example, I say, but there have been a good project wherein one of the Bombay Regional Development Authority, MMRDA, they saved about close to 80 crore rupees by removing rock shed and moving towards barrier. So again, like I said, it requires a lot of what you call it, a gut feeling, more than I would say, more than a gut feeling to really, especially for such large departments to, revise the design. So what over here is I have shown locations 1, 2, 3, 4, 5. I'm back to my site again, 5 locations. And I just would like to speak on the highlighted portion. So location 1 shows some drapery system. This is a mesh system. And I would also speak a bit on flexible rockfall barrier. These are the two, of course, two important things which are latest. Should I say rockfall barrier is the latest technology? I can definitely say it is the in thing happening, with the extreme weather events happening and more infrastructures which are closer to, such steep slopes. You are actually looking at more and more use of these two highlighted portions. So in this site, what we saw was there are other protection methods which have been used. For example, what you see is railways had used shotcrete. Now, one experience we have learned over the laterites, as I say, the residual soils is residual soil. If you want to cover residual soil with shotcrete, it doesn't work because the shotcrete material tends to part away from your rock or surface which has a lot of residual soil as well. So that is because even I would say rock surface itself, you have to be careful because in a way you're providing a barrier over the surface to prevent the pore water from escaping. So you actually are creating unless the tubes are there, proper drainage facilities are properly checked each year. But by providing such a cover, a coat over it, the pore water pressure behind you're preventing that pore water pressure to dissipate. So you see a lot of parting away as shown by these two photographs. So this is again something, it's not a very long lasting, maybe 3-4 years you need to go back and do it. But like I said, many departments, they would like to do it, shut it and forget it. So that is something, of course, it's a thing we got to learn. Now, the design criteria for mesh system, at least for drapery mesh system, is very simple. It's straightforward. You have a slope and you, on the right hand side figure, I'll just show you an example. You estimate what is the debris. You allow the debris to accumulate at the bottom of the slope. You use the weight of the mesh on the slope and the rock bolts which are holding onto it. And straight away you can in fact calculate what is the factor of safety. So there are, of course, guidelines are available, and I've seen many people design this using a very simple method of doing it. You can always, of course, use some kind of computer-based program, but I always believe hand calculations is the best, wherein you want to simplify your geometry to begin with, and of course look at it as a more like 2D problem instead of 3D problem. But of course, for complex geometry and wherein you would of course have to use some kind of computer-based program and estimate the factor of safety both for again stabilizing and destabilizing forces. So in general, it has been seen that the mesh, the mesh which you use, you need to use what kind of ground, friction is, because the ground itself will provide pretty of help to resist the mesh from moving in. So keeping all that in mind, you can design this. sorry, these are the input parameters. I'll skip this because for now, I don't think we are going too much into this, but these are, of course, certain assumptions are used. Of course, I think I wanted to highlight assumption meaning, again, what is the thickness of the weak layer you have? That is one important assumption. Your joint inclination, and your of course what is the friction between the anchor and the rock. So these are few input which you need to see based on your local geology. In this case, finally, I believe we used what do you call it, for these locations, we used anchor bolts installed at 2.5 by 2.5 meter, which was used to hold the steel composite wire mesh. Okay. A rockfall barrier is, which is here on the right hand side. It's like a mesh itself, but a standing mesh. Of course, the design itself is different, the height is different, and you need some kind of energy absorbing, what do you call it, dissipators as shown in the figure. So it's like it's like a very flexible, should I call it retaining wall, but it's a flexible barrier system. Okay. So there are several parts to it. Now, I would say because it has come to us in the last decade or maybe decade and a half maximum. Much of the components are something which we follow are based on European standards. So we are based on maybe in about 5 to 10 years. Once we learn more about this, we will have our own standards coming up. Our own experienced people with the local knowledge will do much better as what we are doing now. But until then, what we are doing is we use the components and parts which are again in reference to certain international specifications. So much of the material itself, I would say, which comes in, for example, the support structure, the connection component, and the interception structure, which is shown on this table, all this is mainly, I would say, imported. Okay, but like I said, this one, we will eventually have our own system of development in years to come. So in this case, we used the barrier system, which met the specification of ETAC 27. They have used the protection kit, and they have tested it to higher energy level of, I think, over 10,000 kilojoule. We used it for our design purpose right from 1,000 to 8,000 kilojoules. So 8,000 kilojoule, let me just tell you, it is huge. Okay, you're looking at something like a couple of tons of a rock piece falling from a large height. And then also whatever design you do, you have to also see that there is an amount of elongation and flexibility involved. Now, in this case, if I use a smaller, what do you call it, energy barrier, I would need to see that because of the flexibility, the material does not fall over the railway track. So I have to also see, other than the required energy, I have to also see how much elongation will happen. And due to that elongation, do I need to go for a higher energy barrier? And the height, of course, needs to be designed to prevent all the boulder trajectory from moving up to the road. Now, the design of these barrier systems is again very simple, straightforward. You can do simple and potential energy. You can use that, but of course you need to see that the ground friction and the terrain itself will somehow kill a part of the energy. If you start designing everything by, say, MGH, you will end up by a barrier system which will be not at all workable. And of course, you also will not be able to capture all the rocks, because you need to also see which rocks bounce, which rocks you are able to trap based on the location of the barrier. So if you have the energy of the barrier, again, the potential energy moving down to kinetic, and because of the rotation, if you allow rotation, you also have the angular velocity and the angular momentum and the, of course, the energy component coming up. Okay. And there are several tools available. In particular, because this rockfall event is more like a statistical event, so there are quite nice tools available to determine both in 2D and 3D what kind of barrier system you're looking at. So this is again like in this computer program, you start looking at what is your where you want the barrier to be placed and what is the size of the boulder. You estimate based on the past history and the whatever is available on the terrain. Your boulder size, if you locate the position of the barrier on the slope, you see where the detachment points are, and if you're able to capture more than 95 or 98%, depending upon how what do you call it, how well you want to your probability of missing the barrier you want to minimize, you can then whether say it is safe or not safe. So it's a very simple, I would say, step block diagram wherein which helps to estimate. Now, these are screenshots. So some of you, if you have used this software, you would immediately recognize the software based on this. If you do not recognize, then I would say you're free to use any other because, whichever you're comfortable with. But there are several you can try. In fact, we have even tried using a finite element based on, not finite element, I'm sorry, based on DEM. And we got some interesting results at that time. So over here, for this site, for example, you are recommending a 2000 kilojoule capacity barrier, which is 5-meter height. And a span of this is 130 meters. That is one particular section wherein you probably would recommend. Now, after this, of course, when the proposal came in, it came with a big bang, but of railways having a budget of close to 60 crore rupees for this. But at the time of actual implementation, if you see the bottom highlighted, it is not more than 6 crores. So it ended up not the protection of all the 5 sections, but just let us choose one section which for as a trial basis to show that whether the system works. So this is what the tender document came out. I think it came out in 2019, and then after the tender process, COVID came in, and this whole thing construction happened during the post-COVID period. What you see is people even during COVID period, a lot of people started to work. But this is interesting. These photographs. This site, like I said, was randomly chosen as the first site. Let me just go back. This is a tender randomly chosen, for the first site. Railways did not know what will happen. They did like, what you do, eeny, meeny, miny, moe. Which site do we choose? So they said, let's do this with 6 crores. Let's do it with this site. And once constructed, just the year after, wow, it really did its job. Some of you, if you look at these photographs, if you see down there on the top left photograph, you may faintly see the railway track down there. Yeah, I hope you can see this. And all the debris, rockfall debris, what you see is it has captured it. Of course, there is some shattering happening over there. And some people make I say these photographs are a success and a big learning curve. Because they of course managed to hold the material, number one. And my argument is, yes, they got damaged, but they did the job. Damage, of course, we learned. That was a learning experience. But I tell you, the railways were really proud that they had chosen the right spot at the right time. And post 2023, what happened was its history. It became of course, the railway engineers were awarded. But more importantly, railways, this was something which railways decided to take it as a long-term project for all other sites. And even today, even this monsoon, there are other sites wherein the railways have started to use the barrier system. So it's a success, I would say. Sorry, my finger touchscreen zoomed in. I'm zooming out. Okay. Oops. Sorry, my mistake. Yeah. So, yeah. So the end of story of part 1. I just would like you to look at this in a, because the entire range, if you're not part of this world, you will appreciate the entire range is so beautiful. It's such a nice view. And this drone picture actually captures the whole thing. So you see 2 tunnels over there, and then the tracks which are coming from the left side of the hill, and far other end you can see the tracks, extreme other end, which are coming from the other side of the hill, and then they merge together. So this is your Monkey Hill. It's so beautiful looking, and in monsoon the whole system becomes cloudy. In fact, as I speak to you today, it's raining heavily outside in Bombay region, and my entire area over here is become very cloudy. So I welcome you to see this. It's huge. It's very nice. Let's move on to the next site. Okay, the next site was again based on the learning curve. This site lies along the Mumbai-Pune Expressway. Previous to this, meshing had been done. Of course, depending upon the scale of the problem, and of course the design at that time, and more importantly, I would say the maintenance from that time to this time. You have to see whether new problems emerge at the new site or the old site. So at this particular site, a steep slope had failed. It happened after heavy rainfall, and this failed surface reached the road level. If you travel along Mumbai-Pune Expressway, this is major highway. A small stoppage will be headlines and in the next day's newspaper. It's a big road connectivity between the 2 cities. The geology is quite complex over here, and it has interbedded layers of pyroclastic material. These are pyroclastic material, kind of, I would say, during the formation of the rock. This is the ash kind of material which probably flew along with rock pieces, and rock pieces, once it flew at the time of volcano explosion, they probably got deposited, and then layers of other rocks were formed. So what you see is interbedded layers. This is the weak material. And during monsoon erosion, as the surface rock starts to erode, this material erodes pretty fast. And you see, like I said, 2-3 years of monsoon, it's fine. And suddenly you see one big chunk fall down. So this is what the material, like laterites, you also have this material, which is ash, mainly ash and unbounded. So for this site, we again used the photograph on the left. In fact, the cartoon on the left shows what the problem is. There's a car, and you need to have a barrier system with at least 12 to 14 meter clear spacing, and a higher capacity, if you see, was chosen because of the flexibility of the material. If you have higher capacity and low material falling down, elongation will be less. So you have to play around with these terms, with these different combinations to get the right material. So over here you see a lot of meshing being done, and of course the barrier is not shown. But if I have a more recent photograph, you would be able to see, or if you travel along this stretch, as soon as you come out of the tunnel, you must thank IIT, because if it is working, you thank IIT that IIT did a good job. But if it has collapsed, you can definitely blame the contractor that it is not the IIT, but the contractor did a bad job. Okay, sorry, that was a poor joke, but let me move on. So this is again, like I said, just to put it in English, what I just said, you had self-drilling anchors, 8 to 10 meter long, and in this case they use resin. And of course, if you are using resin, you are also free to use cement grout of low water cement ratio. Important is to use large bearing plate, because you have a lot of loose material and you don't want local failure to occur just behind the bearing plate. You have again, I just said there is a row of flexible barrier which are installed, and these barriers were installed for service energy levels. So service energy means you don't want them to be destroyed because of the impact. That this is service energy. Otherwise, they can be designed to fail upon impact. This is a very nice video, and if you are half asleep by now, I would request you to wake up. This video, I would say, is the only video which you will see on this. I doubt whether it's freely available. It's in Nagaland, Dimapur Kohima highway, like I said, and this highway runs next to a hill. The locals call this hill as Pagla Pahad. You know, Pagla is Hindi word for mad or crazy. Is because locals, they say for no reason they see rocks falling from the top. You know, rocks, pieces, debris, it falls from the top. So they call it as Pagla Pahad. It's a major highway. What you see in front, I'm going to run this video. What you see is there's a road blockage because beyond a kilometer after this, a lot of debris had fallen, and over here the entire traffic has been stopped. You're going to see a very big boulder fall on the black car. It's going to roll over and it's going to damage the remaining two cars. So if you are slightly emotional based, I would request you to not to watch this, because it is, where did I go? It's really it happened all of a sudden. I'm going to run this again, but there is going to be a recap of this video. Sorry, I'm going to run this again. Play. This video was taken by, a dash camera. It's reverse. You're going to see the boulder come down at a very slow pace, frame by frame. It hits the first black car, and then the Wagoner. It takes the Wagoner down the valley. Wagoner people died because of this. The whole family died. And you see another boulder coming right to the truck level, front of the black car. It has carried another white car. Okay, now comes the surprise part. Just watch carefully. The people in the white car, one person died. The Wagoner, all died. Now you look at it, the black car, which took the first impact. Look at the black car, please, carefully. People are coming out of the car. Nothing happened to them. They were very plain lucky that the rock fell on the backside of the car. Of course, the car manufacturer would have taken this video as that the car is fail-proof. So this is again quite a interesting piece, and I'll show you how the rock in fact fell down. The video is pretty long, but it shows the likely track the rock took to reach the load level. Now this is interesting. What I meant to say was this is not a two-dimensional problem. Again, I'm reversing. This is the reverse. Because the rock travels from one section, and then if I move forward, it travels to the next section, to the next section, and to the next section. It is not straight down. So this is what I meant to say was it is not necessary. I must say that it is you should have the proper geometry, the profile. So it is not necessary the rock will always follow a 2D space. Okay, let me move on. So the problem is the entire Kohima area has sandstone layers which are separated by weak infill material. These sandstone layer sheets of sandstone are very steep, 60-degree here, and the infill material is too weak. So you can see the interbedding layers really they are like dying to fall, and they crisscross each other. And what is important over here that the project report, the initial project report, unfortunately had only 3-meter high breast wall. You know, the rock cutting, it was not properly, I would say the report DPR had to be proper. and the height of this breast wall was also insufficient compared to the cutting. So this is again what we see is, the tender documents are prepared by DPR, and of course, then the problem starts to come in when at site condition are quite different. And this is what we see. Even the Chandigarh-Shimla highway, I think the same thing over there. The tender document missed important things. I would say the DPR missed important things which were not in the tender document. So having a good project report at the start of the project is important. Okay, now you need to be, this is something which controls the, whether it is die or I would say live or die for any project. This is the last slide. I just want to show that, this is, I would say, an application wherein it is not necessary you're looking at protecting expensive property. Over here, you're protecting slum area. This is, of course, in like any urban, I would say, city, it's a problem because the slums are very close to the hills, and the hills are like, part of the hill are prone to disintegration during monsoon. So over here, to protect the slums, a high energy capacity barrier has been designed and installed. Of course, psychology of the local residents has to be taken care of in the designing and in the height. So much of the, I would say, design and height is controlled by the psychology of what people are there, and of course, how the politicians try to control this or try to appease the larger mass. So this is just a last application I wanted to say. My concluding lines are, a single solution to prevent damage is not enough. Definitely doesn't work. You can minimize the maintenance as in any other, solution, but it will not be eliminated. It has to be annually checked both before and after the monsoon, especially because of, the large scale events happening. So with this, I would like to thank you. Thank you very much for listening to me. If you permit, I can stop sharing.
Yes, sir, you can stop sharing. Thank you very much, Dr. Juneza, for giving us such a beautiful presentation of various rockfall mitigation measures with the help of several case studies. Thank you very much. So with this, we'll move to our next speaker. So our next speaker is Dr. Satyajit Patil, Associate Professor at SVNIT Surat, who will share his knowledge on sustainable pavement solutions using geogrid reinforcement and industrial waste utilization for eco-friendly roads. So Dr. Patel specializes in geotechnical and geoenvironmental engineering with key research in industrial waste utilization, geosynthetics for pavements, and sustainable ground improvement. He holds 2 patents and 36 international publications. Please welcome Dr. Patel. Over to you, sir.
Thank you.
So, sir, I have to help you in the presentation. So I'm making my mute and I'm going to repeat.
Okay, so good morning to all of you. So, shall I put down my camera? I think that will be better. Yes. Okay. So, whether it is full screen?
It is, sir. It is full screen.
Yeah. No, it's okay. Right. Yeah, so I am audible?
Yes, sir.
Yes. Okay. So I will discuss regarding the utilization of the geogrid in the road pavement, particularly for the flexible road pavement, and how we can use the industrial byproduct also in the road surface layer reinforced with geosynthetics. So that I will discuss. we have constructed some test sections as a part of the state highway. So that we'll discuss the field test result and how to evaluate the performance of the geogrid reinforced layer. And also I will discuss the cyclic plate load test. So introduction, objectives, then construction of the test sections and field testings, result discussion, its summary, then cyclic plate load test that is recently developed by ASTM in 2022. So how it is more useful to evaluate the MIF and LCR value of geogrid reinforced pavement. Then concluding remarks. So introduction, that is due to rapid socio-economic development, construction of road network has gained momentum in India. So there is huge massive construction of road is going on throughout India, various national expressway, NH, state highway, all these roads. So therefore, there is a scarcity of suitably graded conventional material, that is stone aggregate, for pavement construction. Huge quantity is required. So obviously there will be scarcity. And also the hauling distance is increasing day by day. The cost of extracting good quality natural material is also increasing. The basic aim of the study is to reduce down the amount of costly bitumen layer as well as natural aggregate layer by reducing the thickness of bituminous layer using geosynthetic reinforcement mechanism in base and subbase layer, and improve the engineering characteristics of base and subbase material. So the bitumen layer is the most expensive layer in the road pavement. So if we will be able to reduce the bitumen layer by 20, 30 mm or 50 mm, it will significantly reduce the cost of pavement. So that can be achieved by the use of geosynthetic material. So currently no detailed information about layer coefficient ratio or modulus improvement factor values of geosynthetic reinforcement are given, and no design charts are available in India for the use of this material. So limited data are available, and as per the IRC SP 59, some guidelines are there regarding LCR and MIF, but I will discuss its limitation and how we can improve that value, and we can improve the more, we need to carry out more research on that. That I will discuss. The outcome of this study will help to develop LCR or MIF values with considering type of geosynthetic, then design charts for the use of geosynthetic in flexible pavement. So the various type of geosynthetic, like if you use geocell, geogrid, steel wire mesh, are there usually used in the road pavement. So how we can get the more accurate value of LCR for a long-term pavement performance, and how to prepare the design charts. So there are a few data available in the literature. In that paper, Bodhanam et al. 2025, they have shown some cost comparison of geogrid reinforced pavement. So for 6% CBR, they have obtained the cost saving of around 20% per lane kilometer for PP30 geogrid and 24% per lane kilometer for PT80 geogrid. So you can see the huge quantity of cost can be saved, 20 to 25%. It is a huge quantity, around 20 or 25 lakhs per kilometer per lane by using geogrid, and the bituminous layer thickness has also been reduced. Next. So the objectives of our present study, that to design the test sections using CBR of the subgrade CBR at the site, then traffic intensity as per the IRC 37 guideline, and determine the critical strain of all the design test sections by conducting numerical analysis in ITPEP. We can check that strain value, and you can check our design or cross section. Then to construct the 18 different test sections with different types of geosynthetic, that is, we have used geogrid, geocell, and steel wire mesh, and study their effect on the performance of this pavement. To study the effect of tensile strength, aperture size, location of geosynthetics on the performance. To investigate the initial performance of the unpaved geosynthetic reinforced test section by in situ testing using lightweight deflectometer, which we can use for subgrade and subbase layer, that is unpaved, and by conducting field CBR test also on the top of subbase and top of base layer, comparing the result with that of unreinforced section. Then after completion of the road construction, the field performance has also been evaluated using the falling weight deflectometer. So which gives the overall performance of the whole pavement, including the bituminous layer. Then to develop the design charts for the geosynthetic reinforced flexible pavement, whatever results or MIF or LCR value we have got, or the improved modulus we have got, based on that we can prepare the design charts. The methodology, design of the test sections using IITPAP software. Test section has been designed, or cross section has been designed using the subgrade CBR and design traffic, construction and quality control of 18 test sections. Then initial field evaluation using LWD and field CBR. After that, development of composite modulus improvement factor from LWD test result. Estimation of modulus value for test section using long-term falling weight deflectometer has been carried out up to 2 years. Then calculating the MIF and LCR value from the FWD modulus. Then design charts has been developed. Next. So this is the Google Map view of that road section. That is where the construction has been done. That is part of the Sahol Kim State Highway near Surat. So we have divided the whole area into 3 zones. At the zone 1 and 2 are just beside of each other. Next one. And zone 3 on the slightly around 50 meter away on the other side, right side, and one is on left side. These are the sections. That 18 different sections we have constructed. That is given the name S1 to S18. So at various sections, we have used the various materials, various geogrid materials. That is S1, section 1, that is single layer geogrid. That is geogrid tensile strength is 20 kilonewton, aperture size is 32 into 32. That is placed at the center of the base layer. Center of base layer WMM. The chainage of that section. The length of that section is 50 meter length, and the width is a one complete length, that is 4.9 meter length width. And cross thickness has been designed as per the IRC code. The various thick layer, that is bituminous concrete 40, DBM 90 mm, then bituminous macadam 65, WMM is 250, GSB 400. So the then S2 is the conventional control section. So to compare the material with control section, that is necessary to construct the control section also. Then only we will be able to get the MIF and LCR value. So the length and cross thickness is given for each section. The S1, S2, S3 single layer geogrid, and at center of GSB sub-base. Next. So these are sections S5 to S9. The geogrid, the 40 kN geogrid is also used. Aperture size 38 into 38. Then S7 is geocell, 150 mm height, bottom of subbase. Geocell, bottom of base. Next. S10 to S14 geocell. Then S11 is the steel wire mesh used at the center of the base layer. Then geocell with filled up with fly ash also, that is S13 or S14. That S14 will be the geocell filled with fly ash. Next. So S15, 16, 17, that is geogrid. Center of that is aperture size is different. Next. So these are the typical cross section of this control section, the various section. Next. That CBR is 3% and traffic is 30 MSA. It is designed. So you can see the cross section. The geogrid is placed at the center of the base layer, center of the sub-base layer. Geocell is placed at the bottom of base and also bottom of sub-base layer. Next. Next. So this is the actual photograph of the site. You can see the site is completely waterlogged. The drain is there. So it is completely muddy soil or quite slushy. The CBR value is less than 0.5. You can see the figure. it is completely waterlogged. So that's why we have used the subbase of 400 mm thickness subbase. So out of this 400 mm thickness subbase, 200 mm will go penetrated inside the subgrade only, inside this soil. So that's the thickness of subbase is taken higher side 400, and effective CBR has been obtained at 3% only. Next. So you can see the type of soil is low plastic clay, CL category, liquid limit ranging from 26 to 25. Next. And granular material used for the base and subbase layer stacked at the site. The particle size distribution curve for GSB layer as per the Codal guideline. Next. Then GSB of grade 5 is used, and WMM it fall well between the upper and lower range. Next. Then fly ash has been used in the subbase layer reinforced with geocell. This is the photograph of the fly ash layers. That UCS on-conflict strength and also triaxial has been done on the fly ash to get its angle of friction and all the parameters. Next. The compaction curves for the fly ash, then load deformation curve from the UCS test results, the 7 day and 20 days curing period. These are few photographs of that your geogrid, geocell, and glass, that your steel wire mesh. You can see the geogrid, geocell, and steel wire mesh. Next. So they are the mechanical properties of the geogrid. So we have used both 20 kN and 40 kN. The various properties are there: tensile strength at 2%, tensile strength at 5%. Next. The other properties of the geogrid, then road mesh, steel wire mesh. So yes, next. The few photographs during the constructions, you can see it is completely waterlogged. So when we have put the 200 mm GSB, so that goes inside the subgrade. So that is considered as the subgrade layer, the first 200 mm GSB. The upper 200 will act as the subbase layer. Next. Few more photographs during the constructions. Next. Next. Yeah, okay. So they are the previous one. Yeah, so that field testing during construction, the field density by sand replacement method, the compaction laying of bituminous layers. Next. Yeah, after the construction of the road, the completion of the road, the photograph of the image of this road. Next. So the test locations that we have done the field CBR and lightweight deflectometer and dynamic cone test also to get the CBR value at different locations for each section at 5 meter interval on both that left inner wheel path, middle, and outer wheel path. Next. The dynamic cone penetration test as per the ASTM D6951. So you'll get the CBR value from the dynamic cone penetration test. So that has been carried out on the subgrade and top of subbase layer. Next. The lightweight deflectometer has been done both on the top of base layer and subbase layer. So from lightweight deflectometer, we will be able to get the composite modulus. Composite modulus of both subbase plus subgrade, composite modulus. Next. Then arrangement for the field CBR test at the site, just using a simple hydraulic jack and proving ring, we will be able to get the field CBR test. Next. Then falling weight deflectometer instrument, which is available at SBNET Surat, made by Dynatest Denmark. So that has been used to evaluate the field performance of the complete pavement, whole pavement after the constructions. So starting from August 2019 to July 2022. So 3 years we have tested the pavement at different load has been applied, 40 kN and 55 kN and 70 kN also. Next. So these are the instrument at the site, testing is being carried out. Then from that falling weight deflectometer, we will be able to get the modulus of each layer. Modulus of each layer. Then you will get the MIF, modulus improvement factor, average modulus of reinforced layer by modulus of unreinforced layer. From MIF, you will get the LCR value. The equations are given in the STO code and also IRC SP 59. Next. So they are the DCPT, dynamic cone penetration test result. You can see the CBR value in the subbase layer range between 15 to 25 because the subbase is resting on the very your slushy soil. So that's why the CBR is quite low. Next. Then the composite modulus obtained from the lightweight diffractometer. You can see the composite modulus at for various interval at 5-meter interval at 11 different points, inner, outer, and at the center line. So modulus range between around near about 20 MPa. This is a composite modulus, means combined modulus of subgrade and subbase layer. That's why the value is low. Next. Next one. Yes. So that composite modulus from LWT compared with top of WMM and top of your GSB. For top of WMM, the composite modulus range from 27 to up to 64 MPa. It is also composite modulus. From LWT, we will get the composite modulus only. We have not done the back calculation analysis. So, and on the top of subbase, the modulus is in the range of 20 MPa, composite modulus. Next. Then from this lightweight diffractometer test, and from we have got the composite modulus, and from that we have got the composite modulus improvement factor, CMIF. You can see the value for 20 kilonewton geogrid and 40 kN geogrid. The CMIF, when it is used in the base layer, the MIF value is higher, 1.58. When used in the subbase layer, it is on the range of 1.19. So if you use the geogrid in the base layer, obviously the MIF will be more because the stress is more at the base layer. So it will be more beneficial for use the geogrid in the top layer, base layer. So, and for the bottom one table of different aperture size, 38 and 65. And we can see the MIF value 1.7 and 1.53 for the 40 kN geogrid. Next. Next one. Okay. Yeah, previous one. For the geocell of 100 mm height, 150 mm height, geocell, you can see the MIF value is slightly higher than geogrid. MIF value is in the range of 1.8 to 2 composite modulus MIF value. When it is used in the base layer, it is 2. In the subbase layer, it is 1.8. So effect of geocell reinforced fly ash has been used in the subbase layer, reinforced with geocell. So MIF value for a fly ash reinforced geocell, fly ash reinforced with geocell is 1.23, and for fly ash reinforced with geocell of 100 mm height is 1.13. Next. So these are field CBR test results. You can see when the compared the field CBR test result of all the type of geosynthetic material with comparison to unreinforced section, you can see the load deformation diagram. The bottom one is the unreinforced one there, and all the material has given the higher CBR value. Next. You can see the value here, the CBR value, and for the load deformation points. Next. So the CBR value for all the 5 different geosynthetic material. So with increasing rod depth, obviously load will be more, CBR value will be more. It has increased more. Okay, next. So these are the modulus of base layer obtained from the falling weight diffractometer test. So you can see here the modulus of the base layer range in the range of around 140 to 160 MPa for the reinforced sections. Whereas for the control section, if you see S2, S9, S18 in the control section, the modulus is in the range of 100 MPa, the base layer. So the modulus improvement factor has been obtained in the range of 1.4 to 1.5. Next. So this is the modulus of subbase layer. So the control section is in the range of 60, and for the reinforced one, the modulus is in the range of 80 MPa. It is tested for 3 years. Next. And this is the modulus improvement factor from the FWT testing, which we have see the figure. So for different geogrid tensile strength, the MIF value is obtained from lowest is 1.25, maximum is 1.6. 1.25 to 1.6 modulus improvement factor we have obtained. LCR value is also obtained like that. For different aperture size, different your tensile strength. Next. For the design chart, so subgrade CBR and traffic on reinforced section cross section has been designed as per the ASCII 37. Then MR value or resilient modulus of base and subbase ciliar as per the ASCII 37 can be used, and you can get the vertical strain and horizontal strain using the IT PAVE. Next. Then structural layer coefficient. So after getting the control section, now you can use the A2 and A3 value based on the modulus value. Then take the modified structural layer coefficient by multiplying with LCR value. You will get the modified modulus. Then you will get the reduction in thickness, and you can try with IT PAVE to check that the strain will be safe. Next. So by using that improved modulus of the base and subbase layer, we can develop the design charts. Like for on reinforced, this is the thickness 380, 250, 90, and 40. So when you reinforced with 20 kN geogrid, 32 aperture size biaxial geogrid, this will be the thickness 230, 250, 50, and 30. So this is for 10 MSE design traffic and 3% CBR. So similarly, for different CBR value and different traffic intensity, you can develop the design charts for the reinforced section with different type of geosynthetic. Next. This is for 30 MSA design traffic and 3% CBR. Similarly, the design charts has been developed using the IT PAVE and the improved modulus. Next. This is for geocell reinforced sections design chart 20 MSA and 3% CBR, 30 MSA, 3% CBR. Next. So these are the conclusions from this field test, that we have seen that the modulus improvement factor has been achieved up to 1.6. For geocell, it is up to 2 when it is used in the base layer. So you can get the higher MIF value when the geosynthetic reinforcement is given in the base layer as compared to subbase layer. Next. Conclusion from long-term falling wave deflectometer. So higher FWD load, that is 70 kN, significantly increased modulus value in both geogrid and geocell reinforced base sections. As the higher will be the load, more will be the tensile strength occur in the geosynthetic. So more will be its MIF value or the bearing capacity. Next. Okay, so the limitations of FWD testing. So in this field test, we have obtained the lower value of MIF, that is 1.5, 1.6, which is quite low as per the guideline of IRC SP 59. So where it occurs. So these are the limitations of FWD testing. So geogrid tensile strength is low at lower axial strength and increase linearly with induced axial strength. When more tensile strength will induce in the geogrid, its strength is more. So heavy vehicle cause permanent deformation or rotting, which induce the significant axial strain in the geogrid. This leads to mobilization of geogrid tensile strength, improving the pavement performance and influencing the LCR value. But in FWD testing, it captures only elastic deformations using geophone during a single load cycle. We cannot measure the plastic deformations or rotting in the FWD testing. And also we cannot apply the FWD testing repeatedly. We can apply a few thousands only. We cannot apply up to 50,000 or 1 lakh like that load applications with using FWD. So using the back calculation technique in the FWD, it gives the modulus value. So but we will not get the proper benefit of geogrid reinforcement by FWD testing, because your strain induced in the geogrid is very, very small. The deformations in around 1000 micron to 1200 micron in the FWD testing. There are no rotting or permanent deformations will occur in the few cycles. So that's why cyclic plate load test is very, very necessary, and it is recommended for determination of LCR and MIF value, which because cyclic plate load test will induce the rotting or permanent strain at the top of base layer or subbase layer. Next. Then cyclic plate load test developed by ASTM code in 2022 in the standard. It gives the detailed test procedure, and IRC SP 59 also recommend the field CPL test to calculate the LCR MIF value. The scope, you can carry out this test on both paved and unpaved road with or without geosynthetic, and you can compare the field performance. The performance is measured by the structural improvement, how much improvement has been occurred for the geogrid enforcement that you can obtain. Cyclic plate test is intended to be performance test conducted on unpaved and paved road cross section. It is a tool to compare the different type of geosynthetic, different type of soil type, the strength, the thicknesses, and construction of procedure for a variety of pavement application. Next. Its significance and application. This measures the geosynthetic benefit and also any pavement material because it simulates the traffic loading very closely. So we can evaluate the performance of any pavement material with this CPL test very accurately. It is recommended by Astute R50 also, and test procedure and the analysis method is also given in IRC SP 59. The number of load cycle applied by CPL device correspond to number of equivalent single axle load used in ASTO 93 pavement design guideline. Next. So this is a typical your schematic diagram of test setup mentioned in the Banerjee et al. 24. You need a steel tank recommended by ESTM code, and it has your hydraulic cyclic actuator, which is with the hydraulic oil pressure, we can apply the cyclic load. Then control unit will be there, and your measuring, you have to measure the load and the deformation with the help of LVDTs. Next. So the tank size should be minimum, the boundary should be minimum 75 centimeter away from the plate. So minimum tank size will be 1.8 meter total tank size. The tank can be either square or circular also. Subgrade thickness should be in the range of 900 mm. Tank wall should be smooth. And steel plate, we can use the 300 mm diameter steel plate can be used. And 3 LVDT are required as per the ESTM code guideline to measure the deformations, which can be placed at 120-degree angle. Next. The materials, you can use all the materials of the pavement, subgrade, subbase, base, reinforced with geosynthetic, and the asphalt layer. Next. So geomaterial, the construction that it should closely match the field condition, whatever field density moisture content will be there, same should be monitor and control in the laboratory test model also. And the density of base subbase layer can be achieved by using the vibrating plate. In situ measurement, you can do the density, moisture, stiffness, all these things. The layer thickness should be measured properly. Next. The procedure of test. So the cyclic load of 40 kN. 40 kN is the standard axle load. So we can apply the 40 kN load and minimum 0.5 kilonewton and maximum load is 40, minimum is 0.5. It varies from 0.5 to 40. Frequency is 1 Hz. That means one load cycle in 1 second. Haber sine or sinusoidal waveform. So one load pulse represent one equivalent standard load. So we can apply the load until surface displacement reach the equilibrium defined as less than 0.01 mm accumulated permanent deformation for applied load pulse or prescribed failure criteria of 20 mm, whichever is earlier. So that is recommended by IRC SP 59. So up to till that point, we can apply the load. So from that cyclic plate load test, what are the various parameters we can measure? One parameter is traffic benefit ratio. So many people have obtained this traffic benefit ratio, TBR, that is number of loading cycle for the reinforced section divided by number of loading cycle for the unreinforced section for a given rutting depth of 20 mm or 10 mm, whatever you can achieve. Okay. So TBR is also the performance indicator. But TBR cannot be directly used in any design guideline or any design of the road sections. Then rut depth reduction. So we can see how much due to this geogrid enforcement, how much rut depth will be reduced. So that percentage you can calculate rut depth for unreinforced minus rut depth for reinforced divided by RDU into 100. Next. We can see the test result reported by Badiga et al. 2021. You can see the cyclic plate load test result in the laboratory physical model. So you can see here, this is a result for 1% CBR at 300 cycles You can see for the control section, rot depth is 3.2 mm. Whereas for reinforced section, they have obtained rot depth of 0.6 mm. So the rot depth reduction is obtained around 81%. So by just simply applying the 300 cycle for a subgrade CBR of 1%, the rot depth has been reduced by 80% by using the GeoGrid. Next. Then determine how we can determine the MIF value for the GeoGrid input base layer. So using the structural number from the ESTO method giving this equation W18 equation. So we need to give the input of subgrade CBR. From subgrade CBR, we'll get the MR, subgrade MR. Then W18 is known to you, that is allowable number of 80 kN or 40 kN single axle load application to cause the reduction and of PSA, that is for the whole pavement life, how much is the number of load axles, that is W18. All the parameters are given in the code also. So when we apply 1 lakh or 2 lakh load cycles up to failure, then we will get the W18 value. From that, we will know the SN value, structural number. Next. So from the structural number and subgrade MR is known to us, W18 is known to us, you will get the SN value. From the SN value, we will get the modulus value. Next. So from the SN value, yes, so this is the graph that is a cyclic Pareto test, Badiga et al. You can see the the top one graph is the for control section. For the GeoGrid input, you can see how much the rotting has been reduced. So for the 1% CBR and for rot depth of 7.5 mm, the control section has taken 3,200 number of load cycle, whereas for the same condition, reinforced section has taken 1,03,000 loading cycle. So structural number has been calculated as 2.58 and 4.5. Next. So from the structural number, the A1, A2, A3 coefficients are given in the ESTO code. Next. So from the structural number, you will get the modulus of the base layer. The modulus of bituminous layer, you have to assume that based on the grade of bitumen, the modulus of subbase layer you can take from the subgrade modulus as per the ASCII guideline. So the base modulus is unknown, which we will calculate from the SN number. Next. So for unreinforced case, the modulus was found to be 336 MPa. For reinforced case, modulus was 1803. So MIF value obtained was 5.4 for 1% CBR. And similarly, for 5% CBR, you can see the MIF value at rot depth of 7.5 is only 1.47 MIF value for 5% CBR. So with increase in CBR value, the MIF value is decreasing. Next. The concluding remarks. What are the limitations of this CPL test, the cyclic plate load test, which is reported in the literature? You can see here. In the present research, geocell reinforced fly ash has been used in the subbase layer. However, other industrial byproducts such as pond ash, construction and demolition waste, stone dust, industrial slag, or any other marginal material which is locally available and quite cost effective or low cost, that can also be used in the subbase layer with the help of geocell or GeoGrid reinforcement. So as per ESTO method, whatever W18 is used in that ESTO equation, that is a predicted number of ESL over the lifetime of the pavement. So cyclic plate load test should be carried out up to failure of the pavement, that is 20 mm rotting depth, to determine the actual W18 value. However, test results are reported in the literature for laboratory and field testing only up to 1 lakh cycle and rot depth of 7.5 mm. In the literature, you will get the loading cycle up to 1 lakh maximum and rot depth of GeoGrid input only maximum 7.5 mm. And they are using the W18 value. But W18 gives the, you will get the W18 value only when you have applied the load up to failure, that is 20 mm rotting depth. So we are using the quite lower value of W18. So lower is the value of W18, lower is the SN value, and lower MIF value we are getting. So higher number of loading cycle or inducing rutting depth up to failure may result in significant increase in MIF value for geosynthetic reinforced pavement conditions. If we apply more loading cycle and more rutting depth, so that may significantly increase the MIF value and it will truly reflect the benefit of GeoGrid. Therefore, it is recommended to carry out the cyclic plate load test up to pavement failure condition to get the actual value of MIF. So for this purpose, SBNET Surat has recently purchased the test setup for a cyclic plate load test, which can be used both in laboratory and field testing to apply large number of load cycles. So we'll shortly plan to carry out the cyclic plate load test at various locations up to say 1 lakh, 2 lakh or 3 lakh or up to failure of the road pavement. So to get the actual value of MIF and to get the true benefit of GeoGrid enforcement. Next. These are the references of all these things used in the present research. Next. 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 Thank you.
Thank you very much. Thank you very much, sir, for your insightful presentation of how industrial waste can be used for sustainable road development. And now we'll go to our next session. Like the floor is open for question and answers. So we have several questions received. So from them, we shall take few questions depending on considering the time. So the first question is from the first session by Professor Babu. So the question was on, can any provision of suitable kind of granular drainage layer or blanket embedded below the top slope protection layer at top level of embankment through which the infiltrated rainwater from top can drain out and keep the embankment core unsaturated and helps to maintain strength of the embankment material more even during the rainy season? Professor Babu?
Rupam, I will try and get in touch with Professor Babu.
Oh,
I think he has left. I will just request him to again join.
okay.
Meanwhile,
Okay.
you can proceed with the other questions
Okay. Okay.
with the other two panelists, esteemed panelists of ours.
Okay. Okay. So this question is from the where we are discussing about the rockfall mitigation measures by Professor Ashish Juneja. So his question, the question is, in Arunachal Pradesh roads, especially from Likabali to Alu and Alu to Doporizu, the rockfall is severe. Will geotechnical net or mesh technique work there?
Okay, I actually am not very familiar with this location, but I am aware there is one project which has been initiated by this state government in collaboration with NHAI. They are in the process of doing protection works. They have done, in fact, several years back, but now they are reworking to improve the system because the existing protection works have fallen back with the severe rainfall which has happened over the last few years. So I think probably if the author of this question can share the location, maybe I can help in identifying, or we can see how this can work. But it depends on the kind of material itself, because if you're looking at net and mesh, you have to see the material itself, whether the anchors can go in, how thick is the weak material, right? And of course the stretch, the height, and the entire stretch of this weak material. So it may or may not be the only mesh may not be the only solution, but in most of the cases we have seen in the in that region, mesh in combination with any other technique has worked.
Okay, sir. So we have another question. So how does the simple free guided type rockfall protection netting system can be compared to the secured drapery rockfall netting system from its suitability, functionality, durability, and economy of the solution?
Okay, so I think the author of the question means is indicating that the free guided would mean that the debris is allowed to collect, accumulate at the bottom in a trench.
Yes.
And in the other case, you secure it so you don't allow the debris to collect at a trench. And occasionally or annually, you open the mesh, unhook the mesh, remove the debris, and then anchor the mesh back again. Okay, in both the cases, it is important to see that whether you have space for the trench. Of course, if you have space for the trench, then open mesh at the bottom is workable. But then also it is important to see that the weight of the mesh alone on the slope itself has to be sustained. So whenever there is an opportunity to provide opening at the bottom, the entire mesh, the weight of the mesh has to be designed in a way that it retains its shape. So there are several aspects. So, but as I see in many cases, even if there is a trench, there is a tendency to hold and lock it up because it is again leaving the what do you call it, mesh open at the bottom. Psychologically, it doesn't provide a better feel. So I would say both are there, yes, but you have to see the geometry of the slope, yes, and so that the length of the mesh itself is important there. But yes, if needed, you can provide an open mesh. That is the answer to the question.
Okay, sir. Thank you so much, Dr. Zuneza, for answering this question. So now we shall proceed to the question from the third session by Professor Satyajit. So, sir, the first question is whether it is appropriate to use the geocell geogrid when CBR is less than 6. If CBR is greater than 10 or 15, the geogrid or geocell is appropriate and economical. Why we shall use geogrid when CBR is 10 or more to reduce the thickness of crust only?
Okay, so if you see the previous some papers in the Indian Geotechnical Journal also, in that they have recommended that geogrid or geosynthetic reinforcement is suitable only for when 5. Okay, but nowadays nowhere the soil with CBR 2 or 3 is used in any state highway or NH. Everywhere in the national highway or expressway they are using the CBR minimum 8, or many places it is in the range of 15 CBR value. So for that also what we have obtained, the MIF value is more than 2 for the 15 CBR value also. So even if the MIF value is 2 or 3, so we are not able to reduce the thickness below 150. Minimum you have to use the 150 mm thickness of WMM. You cannot reduce further that. But if the MIF value is more, you can see the strain will be less. The pavement performance will be more. So obviously, even if the CBR is more than 10, the geogrid will be useful because it gives the MI value 2 or 3. The thickness of bitumen layer can be reduced, thickness of base layer can be reduced. And even if the thickness cannot be reduced further, but you will get the higher pavement life.
Okay, sir. So we have one more question, sir. Can the thickness of base and sub-base layer be reduced more due to the increased value of MIF in case of soil pondest fill geocell reinforcement in the said pavement layers?
Yeah, that is soil. What is pond?
Soil pondest filled geocell means the infill material used will be pondest.
Yes. Yes, so as I shown here, in the subbase layer, we have used the geocell with fly ash. That is used as a subbase layer. It completely replaced the GSB layer. So its MIF value is more than 1. That means the modulus is higher than the control section. So geocell filling with any material like fly ash, pond ash, stone dust will be, the modulus will be more than the control GSB material.
Thank you very much, all the distinguished speakers for today, for answering all the queries of the audience. I hope all the questions has been answered.
Rupam, sorry to interrupt. Professor Babu is here.
Okay, so we can, we can take those questions. Okay, sir. Yeah. Okay, let me go to the questions. Well, sir, we have these few questions from the first session. So the first question is, can any provision of suitable kind of granular drainage layer or blanket layer embedded below the top slope protection layer at top level of embankment, through which the infiltrated rainwater from the top can drain out and keep the embankment core unsaturated, and helps to maintain the strength of the embankment material more even during the rainy season?
Yeah, this is a matter of design. Yes, it can be done, but you need to have a geotextile at the top or bottom. So if the drainage requirement is more, you may have to go for geocomposite.
Okay, sir. And we have also another question. It says, how can reinforcement of soil with natural fibers like sisal and areca nut husk fibers help in long-term basis?
No,
Okay, sir.
long term is something we can't take any chance.
Okay, sir. So thank you very much. And next we can proceed with the next session. So now let us acknowledge the support of our sponsors and partners. So please welcome Mr. Tanmay Chakrabarti, Assistant Director at the Institution of Engineers India, to share a few words on the behalf of our sponsors.
Tanmay sir, you are on mute.
Sorry, now I'm audible, sir?
Yeah.
Yes.
So thank you, Rupam. I will take on from here. So ladies and gentlemen, as we continue with this engaging session of Reinforce 2025, we would briefly like to pause and extend our heartfelt appreciation to the key supporters who have helped make this international event a success. In a global virtual conference of this scale, where innovation meets impact, sponsors are basically the enablers, and their contribution is vital in bringing together experts, fostering dialogue, and promoting sustainable engineering solutions. So I would like to briefly introduce our gold sponsors for this Reinforce 2025. First is Gujarat Maritime Board, GMB. India's pioneering maritime board, GMB, was established under the Gujarat Maritime Board Act of 1981. GMB has led the transformation of Gujarat's 2,340-kilometer coastline through its multiple port development model, with a focus on governance, innovation, and private sector engagement. GMB oversees 48 non-major ports, shipbuilding, and recycling hubs, and promotes coastal logistics and skill development, reinforcing Gujarat's leadership in maritime infrastructure. The second sponsor, Gujarat Metro Rail Corporation, GMRC Limited. It's a joint venture between the Government of India and the Government of Gujarat. GMRC is revolutionizing urban mobility through world-class metro systems in cities like Ahmedabad and Surat. With its emphasis on safety, sustainability, and cutting-edge design, GMRC exemplifies the future of smart and inclusive transport infrastructure in India. We are proud to have GMB and GMRC as our gold sponsors. Their unwavering support is instrumental in powering the momentum of Reinforce 2025. Thank you for joining us for the sponsors acknowledgement of Reinforce 2025. We will now break for lunch. Kindly reassemble virtually for this next second technical session, which will commence sharp at 14 hours IST. I look forward to your continued participation. Thank you.
Thank you, Tanmay sir, for acknowledging the sponsors. So while concluding the first half of the Reinforce, I would like to thank all the eminent speakers and the inaugural session speakers, which includes Mr. B. Vasoya, Mr. V.B. Singh, Mr. N.K. Panda, Mr. Pietro Arbaci, Dr. Ratnakar, Mr. Mustafa B. Shehu, and followed by the eminent speakers, Mr. G.L. Shivakumar Babu, Dr. Ashish Juneja, and Dr. Satyajit Patel. So we thank you all for having your time with us and enlightening the audience. And all the audience include the professionals and engineers, academicians, and at last also I would like to thank Dr. Rupam Saikia, who was moderating for some time on my behalf. And before we break for lunch, so I would like to mention that we have planned for a quick smart quiz, which will happen tomorrow around 3 p.m. And we'll be having three winners for that. So it is just an information today that we'll be having that quiz and the questions in the quiz will be from the content which eminent speakers are speaking about. It will be a MCQ and quick 20-minute session in which a couple of questions need to be answered on MCQ format, and we'll be announcing the winners towards the end of the tomorrow second day. Okay. So thank you all. Now we break for lunch and we'll connect exactly at 2. I would request to the wonderful audience to be available before time, maybe 10 minutes before. And I'll also acknowledge all the speakers for finishing and concluding all their sessions on time. And I would say even before time. And it's like we have already saved 10 minutes. So thank you all. Have a nice day to all. And we'll connect at 2 p.m. exactly.